generation, in that although it is certainly replacing aging coal-fired plants, it's being used increasingly for adding capacity and therefore might crowd out clean and renewable alternatives like solar. What's your view of the next 5 to 10 years for solar installations in light of this trend? And is natural gas a blue bridge to solar or an end in itself?
Yeah. Thank you for the question. Natural gas, with the advent of fracking, has now led to the point where the United States may be a net energy exporter in the very near future, if it isn't already. And fracking is actually a great example of sustained investment over a long period of time that finally paid off. There are a few people out there spinning it as the triumph of the free market, the evidence that government can't do anything right. That's patently wrong. Government invested several hundreds of millions of dollars developing fracking over many years, investing in companies, helping them, and researchers as well, helping to develop this set of technologies that ultimately led to a successful, now viable technology. And natural gas is certainly less CO2 intensive than coal. So by all means, I think it is a suitable replacement step in the right direction. It serves to lower the average CO2 intensity per kilowatt hour. So it's trending us in the right direction. But it alone, unless we perfect carbon sequestration, I know there are a few bright people perhaps here in the audience that are working on that, but unless we perfect carbon sequestration, we won't be able to produce electricity through natural gas at low enough carbon intensities to offset some of the most deleterious effects of climate change. And so I do think that longer term, some even less CO2 intensive technology has to be the sustainable solution. Now, on the basis of economic cost or minimum sustainable price, can solar compete? I believe so, but it remains to be seen, and in what markets and under what conditions. So that's my perspective in a nutshell. I think I welcome and embrace it, but I do acknowledge that it's probably a subject for another talk, a whole Pandora's box of issues, aside from the obvious environmental public safety ones. But, yeah.
Great. Okay, so we're going to open up to the floor, and two young ladies here are going to go around. So how about that gentleman over there first? And then what we're going to do is kind of go back and forth a little bit.
Tremendously enjoyable talk. Thank you. You mentioned black swans. I would like to take that back from KOSLA and give it back to the world as an idea. But what do you see in terms of black swans? Something perhaps in non-semiconductor or some of the new plasmonic kinds of things. An old idea is new again, the idea of nano antennas, for example.
Right. So let me start from the most general sense. The reason a solar cell conversion efficiency is limited to around 25-30%, like I showed in that chart about 3/4 of the way through the talk, is because a single bandgap semiconductor really absorbs light efficiently at one wavelength, at one energy. Photons that have energy less than that energy go straight through, and that's why, for example, glass is transparent. It absorbs ultraviolet light, but it lets visible light through. So when you're driving along, you don't get sunburned, but you can see out your window. If light comes in with an energy above that bandgap, any energy in excess of the bandgap gets lost to heat. It can't be extracted. So you're limited to around 25-30%. That is terribly low. That is terribly low. When you look at the Carnot limit of a 300 Kelvin body at room temperature here, looking at a 6,000 Kelvin body, the sun, you're looking at 89%. And here we are extracting 25% efficiency out of the best solar cell modules, maybe 28% of a single bandgap, more out of the multi-junction devices. So I definitely think there is room at the top to flip Feynman's version. There is room at the top. There's definitely room for innovation. What that technology will look like, you mentioned plasmonics, that is a form of light trapping. That will enable us to make thinner materials, but I don't see immediately how, unless it's coupled to some really new technology, how that will enable efficiencies by itself above that Shockley-Queisser efficiency limit. And nano antenna, again, another form of light trapping. Unless it is truly coupled to new physics, it's not going to overcome that limit. And so what you're looking for is something either new in physics or a new incarnation of proven physics. And one route of proven physics is called a multi-junction device. We make them, we layer one material on top of another, And each layer absorbs a different color of light in the spectrum. So we can make those devices, they're just out of very expensive materials today. So there's kind of two approaches to that black swan theory. One is to say I'm going to take a proven approach, the multi-junction, and I'm just going to innovate on the materials. The other says I'm going to invent new physics. The latter is terribly exciting, also terribly difficult. A lot of smart people have tried for many years.
Yeah.
Excellent talk. We are sitting in the Silicon Valley here with a 50-year worth of research in silicon, thin film, contact resistance. Whole industry got created of $380 billion in the IC business.
Yeah.
Why you doing research now? Can we use all that and go in commercialization and manufacturing right away?
Let me tell you one story of an innovation coming out of the IC world that has the potential to transform silicon, and the reason why it hasn't transformed it yet. I mentioned this epi approach, right, where you take some sort of seed layer, deposit the gas directly on top, it grows a thin layer, you exfoliate, remove the layer underneath, and you're left with a thin, kerfless silicon layer. That is, in essence, the old Canon L-Tran process. It was invented for the semiconductor industry, and it had, gasp, 10 to the 2 dislocations per square centimeter, which killed it from a device perspective for an integrated circuit, but it's 2 orders of magnitude better than what is needed for a solar cell. And so some smart people took that general concept, innovated on top of that, and are developing startup companies, several in fact. Now, that's an example of a technology that made it some step of the way for the IC industry, but then was canned at Canon because it didn't serve its purpose in IC, but yet served to inspire in solar, and now is perhaps yielding some truly transformative tech. So you can't necessarily expect that IC would have developed a technology for solar all the way to maturity because its needs are different than the solar industry. But it certainly is something we're leveraging shamelessly, and it gives us a big leg up on any other material system. Yeah.
Right there.
Hello. What government policies do you think would be most effective at further developing and deploying photovoltaics?
Right. So I am not a policy expert, right? And therefore, I'm perfectly qualified to answer your question, as are we all. Coming from an engineer who knows nothing about policy, I would say the following gap needs to be addressed, and the policy wonks can figure out exactly how to address it, but we need manufacturing in this country to support some of the innovation coming down the pipeline. I've worked with some manufacturers developing new technologies, and it is much, much easier to work directly with them and be able to drive an hour away, visit their factory, help resolve processes, look at equipment, begin troubleshooting together. That's how the oil gets put, the grease gets put into the wheels. Much more difficult if the factory is half a world away. Possible, but much more difficult. Much easier, at minimum, a pilot line nearby. And so keeping in mind what is necessary to innovate, not looking at the world simply from that U diagram of value versus step of the innovation chain of invention over here, manufacturing in the middle, and selling to the customer with branding over here, where you have this U-shaped, and you're like, oh, well, manufacturing, very little derived value. Let's just outsource all of that and forget about manufacturing and focus on the innovation and focus on the selling with an Apple-like logo on our solar panels. There's a gap there in the middle. If you don't have the manufacturing, you're really at a disadvantage on the innovation front. And it's hard for me to express succinctly, but if you visited my laboratory, you would see probably around 70% of the equipment made in the United States, most of it made locally, invented together with them, and now we're using them to help develop new processes for local companies that are manufacturing new types of equipment to manufacture solar cells. And it's that type of cycle that gets broken, right? If you lose the people who actually know how to make this stuff, you lose a critical component to the whole spectrum. Okay, on paper it might look relatively low value, but if you look behind the paper, you can see the supply chain benefits of the manufacturing, all the other people who supply the company that's actually making this commodity product at minimum margin. And that has value. It helps the innovation process. So if I had a message to send to the policymakers, it would be, don't give manufacturing short shrift. Don't just send it packing. Recognize its importance and its instrumental role in the innovation cycle. That's the message I would send.
Hi, we're all here because of the T in technology related to solar panel manufacturing. And it's terrific to see how we can go from $1 a watt to 75 cents a watt to 50 cents a watt. But when you look at the difference in price between the US for a rooftop system, which is like $5 a watt, compared to in Germany, it's $2.50 a watt. It's twice as expensive.
Yep.
And when you try and look at the policies that have affected that, by far and away the biggest factor are what we call soft costs: the permitting, the inspection, the interconnection requirements, the selling costs. How can we as technologists put some pressure on the policymakers to remove those soft costs? Because even if we were to make that solar panel 20 cents a watt, it's still not going to move the needle here in the US.
Right, so very good point. If you want to learn more about the soft costs of solar, a very good report just came out of Lawrence Berkeley National Laboratory. So I would look it up on Google, soft cost installation, LBNL. That's a really good question. I thank you for that. And yes, the difference is stark between Germany, where you have pretty much equivalent of module price, input price to your model. But the delta in what the customer pays for their system is about 2x relative to the US. So on the good side, you might say, well, boy, the installers in the US are really raking it in, that hopefully they're reinvesting in the process and in growing and expanding their capacity base. But my sense, like yours and like LBNL's, is that there's a lot of inefficiency built into the system. Isn't federalism great? We have around 18,000 unique ways to install solar panels. These are the independent jurisdictions with their own sets of paperwork, their own inspection policies, many of which are redundant. And what the DOE has done to try to address this is implement a rewards program, essentially a program that would reward best practices of installation in an attempt to drive down the costs. That's one step short of saying, okay, solar installation will now be regulated like pollution regulation will. And sorry about that. Is that mine?
It is.
Okay, yeah. It's telling me to take my cold medicine. One step is to say, well, we all have the same electrical power. We have 120 volts and 60 hertz frequency. So why not regulate the way we install solar panels nationwide? Do we want to go there? I don't know. Do we want to coax the installers and not the installers, the local policymakers, not so much the national policy, but the local policymakers, to ease some of the restrictions that they've put on installing solar? Or do we want to force them to do so? I'm not qualified to answer that question, but I can certainly see the choice.
Okay, right there. Oh, you got it.
I want to make a comment first. I'm Bob Backrack from Applied Materials.
Oh, great.
Also an MIT and Park alumni. The overcapacity that you talked about is actually a nameplate overcapacity, and most of that equipment is going to be obsolete. So that it's not just a question of demand, but the fact that as the progress in manufacturing goes on, most of that equipment will be, thrown away.
Yeah.
So there's a number of effects at work. So the question was, you highlighted the pyrites, which are also called fool's gold, as a solar cell material. Why didn't you focus more on things like the quantum dot tandem junction silicon or some of the other really plausible, technologies that can get to 35, 40% efficiency?
Okay, so certainly, let me first address your first comment about the overcapacity in the equipment. That's a serious issue, what you just brought up. In our calculations, we're assuming a 5-year depreciation cycle for the equipment in cell fabrication, longer for the module, the wafering, and the ingot casting. And that's because the rest of the industry does it too. When they report their quarterly numbers, they're assuming they're estimating their manufacturing costs based on these depreciation cycles. The reality is that people are changing the equipment in their cell line much faster than 5 years typically. You know well, you're the one selling a lot of this equipment to the customers. And
Equipment actually stays in production for 15 years, whatever its depreciation period. So you'll actually get a long run where depreciation costs are zero.
But in mainland China right now, I believe the efficiency bar is around 16.8, right? If you're not producing a cell at around 16.8%, it gets shoved into inventory. And so there are companies that are taking lines that they just bought turnkey, switching out the phosphorus diffusion furnace, pulling in some other form of junction formation, and bumping themselves up to 18, 19% efficiency. And that was one example, maybe a microcosm of a larger effect. So this depreciation question is definitely an asterisk that I'll put over the entire study. Regarding so-called, specifically you mentioned quantum dot materials. Quantum dots are nifty because if you tune their size, at least in the quantum size scale effects in the range of, say, 1 to 10 nanometers, you can tune the optical properties. But quantum dots have a downside too. They have a lot of surface area, and surface area can serve as a recombination site. We talked about interfaces and the importance of interface engineering. Now you have orders of magnitude increase of the surface area you need to engineer for some of the quantum dot-based solar cells. You're shaking your head. You disagree?
We'll take that one offline.
Okay, we'll take that one offline. Good.
Okay.
Why don't we
Have
move
you
on to the
looked
next
at,
question?
Yeah,
We'll stay here all night talking about quantum dots. Yeah.
Let me ask you a question at the system level, because I'm missing this at the system level.
Right.
So we just said, and so suppose that you reduce the price of the modules to 0.
Yeah.
That's your goal, right?
Well,
Well, no, I'm kidding.
you want to have some margin for the
I'm kidding.
for the module
kidding.
manufacturer.
But let's go to 0. So there we are in Germany,
Yeah.
and he just said that the balance of system costs $1.50 when the modules are 0.
I think it's a little lower. Yeah.
Pick your favorite number.
Yeah,
There's
yeah.
some number for balance of system, right?
Sure.
And we still haven't paid for storage, and we still haven't paid for transmission.
Right.
And in Germany, the capacity factor, as you know, is under 10%. And in the eastern United States, it's perhaps 15.
Yeah.
So now if I do the math on that, with just the balance of system and the transmission and the storage divided by the capacity factor, it looks like I'm vastly more expensive than nuclear. And that's with nuclear not even having gone to the mass production stage yet, which it might do because it might go to mass-produced modules. So if you just run the numbers, I don't see how this works at a system level except in a few locations like maybe Arizona where you're just in exactly the right spot. But if you're in Germany, how does this ever work?
I'm going to quarantine nuclear for now and substitute it for coal, since I can define its costs a lot more clearly. There's some debate about what the true cost of nuclear is. So we'll start with coal. I agree that if you include some of the, some might argue, why don't you include the cost of storage? I would counter that and say the current best practice analysis for how much solar we can absorb onto the grid before we run into storage issues is around 20%. Right? So we have a lot of headroom before we hit that point. What happens thereafter? Well, in certain markets we have headroom before we hit that point. What happens thereafter? I still think we have additional headroom, and it comes in the following form. The trick is not to make solar dispatchable, but to make it predictable. So there's a difference between being able to tell a solar panel, hey, turn on right now. I dare you to turn on a solar panel right now at what is it, 9 p.m. in Palo Alto at this time of year. But what is, I hope, possible to do years from now, perhaps months from now, is to be able to look at the weather pattern, and the same way that we predict the demand for tomorrow to within 1 to 3%, the California CC, I hope that we will be able to predict the output of solar, an ensemble of solar panels, not just one solar panel, but an ensemble of them to within 1 to 3%. If we can do that, then it won't be so much a disruptor as it will be a factor, an input parameter into the calculations of the CEC, and then they pick up the phone and say, hey, natural gas guys, I'm not going to tell you to produce in excess and then shunt to ground or sell at negative pricing. I'm going to tell you to produce just enough so that you guys make money and these solar panels can output their stuff too. I'm hoping that that allows some additional capacity to enter the grid beyond that 20% number that's out there. I think there's still space to grow before we really have to address the storage question in earnest. And that will hopefully allow for some of the new storage technologies, like the ones Don Sadoway came and talked about, to mature to the point where they can really assist the further grid penetration of non-dispatchable, intermittent renewable energy forms.
Okay, one more question from the floor, but I know that professor will stay for a little while longer, so you can come up after we're done and talk. So, yes, back there? Catherine?
Why don't we take two?
Oh, well, we'll do two, okay.
I'll do a brief job. Yeah, go ahead.
Oh, I get to go first. Excellent. Thank you. So regarding the issue of the depletion of the sort of the necessary materials that go into the solar panels, I mean, I understand the validity of the R&D of the different materials, the sort of alternative materials, but where's the legitimacy of recycling solar panels and reclaiming those? Because right around the time that we're going to be depleting all of these, it's going to be about the time they need to be replaced, and when we're going to be taking all of these megawatts and terawatts off of our roofs, and they're going to need to go somewhere, and ideally that's not going to be a landfill. So what's the research on that, if any, and what are your thoughts on that?
Yeah, recycling is already an issue today with certain materials that are potentially toxic, but will certainly become an issue once we reach steady state. Then we'll be able to recycle, reclaim those materials, and put them back into circulation and be somewhat self-contained. Right now, as we're growing at cumulative annual growth rate of, say, 30 to 50%, it's not possible to get all of the new material we need from the old modules that are decommissioned, just because our growth rate's so steep. What's being done right now is traditional crystalline silicon modules, like the one I had right there as a demo. Those are being, there are a variety of forms. Sorry, it really wants me to take my cough medicine. There we go. The traditional modules are being essentially, the trick is to be able to separate the materials out without them contaminating each other. And I was just helping a young lady from Fraunhofer CSU in our laboratory developing a new process to do just that. So there are folks working on it actively. And I hold some hope for it, given the microelectronics industry. They're able to separate materials quite well. There was an HP recycling facility just north of Sacramento. Beautiful facility. Cost has always been an issue, right? And that gets back to our previous questionnaires' point of externalities, adding it all together. So yes, innovation is needed.
Okay, Greg, keep it simple.
Yeah. When you mentioned that 20% that you wanted, say, photovoltaic, what's very important, is that 20% peak power or is that 20% average power? Because if it's 20% average power, you need about 4 times that for the peak power. Because on average, because of the day and night, because of the seasonal changes, you only get about 1/4. And people tend to always use peak power, and it sounds great until you find out what the average is.
Yeah.
So what is that, 20%
Let me
peak or
first
average?
address, this is a capacity factor, and we heard some numbers of 15%, you're quoting 25. Depends where you put it. So that's the capacity factor. And every technology, every energy generation technology has a capacity factor. Even coal plants need to be taken offline for maintenance and facilitization, so they're not 100% either. There's a growing trend in the PV industry to say, well, wait a second, wind, natural gas, coal, these aren't 100% capacity factors. They're reporting their output in watts. Why do we have to keep reporting ours in watt peak and segregate PV from the rest? I would argue, well, there's a good reason we're only 15%. There's a good reason. It's a pretty big difference. It's not like half or 80%. But there's a growing movement within the PV industry to say, let's just call it watts. And then it becomes difficult to distinguish watts equivalent, right? Megawatts equivalent or megawatts. So you always have to be mindful of the capacity factor when you're comparing these different technologies together. To your point about peak power, though, there was a day here in California not so long ago where solar generated around 20% of grid peak power instantaneously near the solar noon. I forget which day of the week it was, but I think it was during a weekday. And this is a growing trend. In Germany, in Bavaria, that number was in the several tens of percents, approaching 50% for one day. I think it was May 27th this past year. So it's interesting to see the effect of very large amounts of PV power entering the grid in select periods of time and seeing the effect of crowding out some of the more traditional generation technologies, especially those that don't turn off very easily, like a nuclear power plant, and force a negative pricing scenario. So this is an evolving issue, and utility companies are beginning to have a backlash against solar because they're ultimately the people paying short term until solar can become truly predictable. Once people know how much solar is going to be outputting on a given day and a given time, people can begin planning around it. You still won't be able to avoid competing with baseload power, but at least the peakers can turn off and avoid negative pricing scenarios or shunting to ground. So lots to evolve, lots needs to co-evolve to be able to absorb this very new, different energy generation technology into the mainstream beyond just the simple, by comparison, simple module. So thank you for your attention tonight. Thank you for your interest in solar, and yeah, do good.
Hang in there for a second. Oops. So we want her to grow up into a better world, okay? And so support MIT if you can through its research, and come on up and talk to the professor.